November 12th, 1938, Tempelhof Aerodrome, Berlin, Germany. Oberstleutnant Werner Baumbach stood in the converted hangar that served as the Luftwaffe's technical testing center, examining a device that represented 18 months of industrial espionage, thousands of Reichsmarks in bribes, and what German High Command believed would be the key to understanding American aerial bombardment doctrine. The object before him, roughly the size of a bread box and weighing approximately 20 kilograms, sat disassembled on a workbench, its brass fittings gleaming under harsh electric lights. This was not a captured bombsight recovered from a downed aircraft. This was something far more valuable. It was a perfect reconstruction, built from hand-copied blueprints smuggled out of the Norden factory in New York by a German national named Hermann Lang, delivered piece by piece through a network of couriers, then reassembled by Zeiss engineers working from memory and stolen technical drawings. The Americans called it their most closely guarded secret. They trained their bombardiers to destroy it, rather than allow capture. They shrouded its very existence in layers of classification that extended from factory floor to bombing altitude. And now, Germany possessed every detail of its construction, every principle of its operation, every mathematical formula that governed its targeting solution. What neither Baumbach nor his superiors yet understood was that this intelligence windfall would reveal something far more uncomfortable than American technological capability. It would expose a fundamental divergence in strategic thinking, a chasm in operational doctrine so profound that having the secret would prove meaningless. The captured knowledge would demonstrate that Germany and America were not merely fighting the same war with different tools, but pursuing entirely different concepts of what aerial bombardment meant, and in that divergence lay a truth that German strategic planners would struggle to accept. The story of how Germany acquired the Norden bombsight design begins not with aerial combat or battlefield capture, but with the mundane reality of industrial manufacturing. Hermann Wilhelm Lang had immigrated to the United States in 1927 at age 26, a German citizen seeking opportunity in America's booming industrial economy. He found work at the Carl L. Norden Company's facility at 80 Lafayette Street in Lower Manhattan, a nondescript industrial building that housed one of America's most sensitive defense manufacturing programs. Lang worked as an assembly inspector and draftsman, positions that required detailed knowledge of the bombsight's mechanical systems. He was competent, reliable, and thoroughly unremarkable in the eyes of his American supervisors. What they did not know was that Lang had served as a stormtrooper in Germany between 1923 and 1927, that his loyalty remained with his homeland, and that he viewed his position at Norden as an opportunity to serve German intelligence interests. In 1937, the German Abwehr, military intelligence service, identified the Norden bombsight as a priority intelligence target. The device had been featured in American military publications as representing revolutionary capability in precision bombardment. Articles described unprecedented accuracy, technological sophistication far beyond anything then in service, and integration with aircraft autopilot systems that seemed almost fantastical to European observers. The Luftwaffe wanted to know if these claims held substance or represented typical American promotional exaggeration. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Oberst Nikolaus Ritter, head of the Abwehr's Air Intelligence Section, made contact with Lang through intermediaries in the German-American community in New York. The approach was careful, methodical, designed to assess Lang's willingness to cooperate without exposing the network if he refused. Lang's response exceeded expectations. Not only was he willing to provide information, he had comprehensive access to technical drawings and manufacturing specifications. Throughout late 1937 and into early 1938, Lang systematically copied every technical drawing to which he had access. The Norden bombsight consisted of two primary components: the sight head, roughly spherical and containing the optical telescope, gyroscopic stabilization system, and mechanical analog computer, and the stabilizer, a separate unit that interfaced with the aircraft's autopilot. Both systems were extraordinarily complex, containing thousands of precision-machined parts, intricate gear trains, electrical servo systems, and optical elements ground to exacting specifications. Copying the complete technical documentation required months of patient work. Lang could not simply photograph drawings. Security at the Norden facility, while not as elaborate as wartime measures would later become, still involved sign-out procedures for technical documents and supervision of work areas. Instead, Lang worked methodically, drawing by drawing, copying dimensions, part numbers, assembly sequences, and operational specifications onto paper he could conceal and remove from the facility. The technical intelligence reached Hamburg through multiple channels. Some documents travelled via transatlantic steamship, hidden in luggage or cargo. Others were photographed and the film smuggled separately. Still others, Lang committed to memory, reconstructing from recollection during evenings at his apartment in Queens. By summer 1938, German intelligence possessed what they believed to be complete technical specifications for the Mark 15 Norden bombsight, the most advanced version then in production. The next phase required Lang to travel to Germany personally. Technical drawings alone, however detailed, could not convey the nuances of operation, the practical knowledge of assembly sequences, the understanding of how components interacted during actual use. In August 1938, Lang boarded a steamship bound for Hamburg, ostensibly on vacation to visit family. His actual destination was a series of meetings with Luftwaffe technical specialists and Zeiss optical engineers. For 2 weeks, Lang worked alongside German technicians, explaining operational procedures, clarifying ambiguous details in the drawings, and demonstrating with his hands how components fit together. He described the bombsight's integration with the SBAE, the stabilized bombing approach equipment that connected the optical sight to the aircraft's autopilot. He explained the procedure for calculating wind drift, the method for synchronizing the mechanical computer's calculation with the aircraft's ground speed, the delicate calibration required before each mission. When Lang boarded his return ship to New York in September, German engineers had everything they needed to construct a working prototype. He also had 10,000 Reichsmarks, approximately $3,500 American dollars, payment for services that would later be described in his espionage trial as selling out his adopted country's most vital military secret. Back in Germany, the Luftwaffe Technical Testing Center assigned the Norden reconstruction project to a team led by engineers from Carl Zeiss Jena, the optics company that already manufactured German military bombsights. The Zeiss engineers approached the task with professional fascination. The Norden represented sophisticated design, genuinely clever solutions to problems of airborne fire control. The gyroscopic stabilization system was elegant, using high-speed gyroscopes to create an artificial horizon against which all calculations referenced. The optical system combined magnification with a wide field of view, allowing bombardiers to acquire targets at considerable distances and then track them with precision. The mechanical computer, driven by electric motors and gear trains, continuously recalculated the bomb's trajectory based on changing inputs of altitude, airspeed, and wind velocity. Most impressive was the autopilot integration. Once the bombardier acquired the target in the bombsight's crosshairs, the sight itself would fly the aircraft, making subtle corrections to heading and speed, automatically compensating for wind drift, and releasing the bombs at the calculated optimal moment. This represented genuine innovation, removing human reaction time from the final critical seconds of the bombing run. By November 1938, the prototype was complete. Not a production unit, German industry lacked both the time and the specialized tooling to manufacture Norden sights at scale, but a functional demonstration model that incorporated all the American device's key features. The mock-up looked remarkably similar to the American original, its spherical sight head mounted on a stabilizing platform, telescope projecting forward, and control knobs positioned where an operator's hands would naturally fall. On that November morning, when Oberstleutnant Baumbach examined the reconstructed device, he was preparing for a comprehensive evaluation that would determine whether Germany should invest resources in either copying the Norden for their own use or developing countermeasures against its capabilities in American hands. The Luftwaffe's evaluation protocol was rigorous. Engineers would test the Norden mock-up under laboratory conditions, verifying its theoretical accuracy. Then, if laboratory results proved promising, they would install it in a test aircraft and conduct operational trials against ground targets. These results would be compared directly against Germany's own current bombsight, the Lot-Fernrohr 7, manufactured by Carl Zeiss and already in widespread Luftwaffe service. The comparison would reveal whether American claims about the Norden's revolutionary capabilities had substance. The German evaluation team brought substantial expertise to the assessment. Carl Zeiss had been manufacturing precision optical and mechanical fire control systems since the late 19th century. Their engineers understood bombsight design principles as thoroughly as anyone in the world. If the Norden represented genuine advancement, German experts would recognize it. If American propaganda had inflated its capabilities, that too would become evident under systematic testing. But before the comparative trials could begin, the evaluation team needed to understand the strategic context in which the Norden had been developed. American and German air forces had evolved along dramatically different paths, driven by different strategic assumptions about how aircraft would be employed in future conflicts. Understanding those divergent paths was essential to understanding whether the Norden's design made sense for German operational requirements. The United States Army Air Corps, predecessor to the Army Air Forces, had committed to a doctrine of high-altitude daylight precision bombing as early as the 1920s. American strategic thinkers, influenced by theorists like Italian General Giulio Douhet, believed that future wars would be decided by the ability to destroy an enemy's industrial capacity and civilian morale through sustained aerial bombardment. This required attacking specific targets, factories, power plants, transportation hubs, oil refineries, with sufficient accuracy to destroy or disable them. Indiscriminate area bombing seemed both inefficient, wasting ordnance on militarily insignificant targets, and morally troubling to American strategic planners who wanted to distinguish between military and civilian targets. High-altitude bombing offered multiple advantages in American thinking. At altitudes above 20,000 feet, bombers would fly above most anti-aircraft artillery effective ranges. Fighter interception would be more difficult in thin air, where aircraft performance degraded. And the bombers themselves, heavily armed with defensive machine gun positions, could theoretically fight their way to targets and back without fighter escort. But high-altitude bombing created extraordinary demands for accuracy. At 20,000 feet altitude, a bomb in free fall would be descending for nearly 40 seconds, covering lateral distance measured in miles. Small errors in calculating airspeed, wind velocity, or altitude would translate into massive targeting errors on the ground. Manual bombsights, requiring bombardiers to estimate these factors and make split-second release decisions, produced circular error probable measurements of hundreds of feet under ideal conditions and thousands of feet under combat stress. The Norden bombsight was America's answer to this accuracy challenge. Developed in the late 1920s and refined through the 1930s, it represented an attempt to mechanize and automate as much of the bombing solution as possible. Instead of relying on a bombardier's estimates and reaction time, the Norden would measure directly, calculate continuously, and release automatically. Its development had consumed extraordinary resources. By the time the device entered production, the program had cost over $1 billion, more than half the total cost of the Manhattan Project that would later develop atomic weapons. The American military had essentially bet its entire strategic bombing doctrine on the assumption that the Norden would deliver the precision necessary to make high-altitude daylight bombing viable. That institutional commitment created enormous pressure to succeed, regardless of whether the underlying assumptions proved sound. Germany's strategic bombing doctrine had evolved along entirely different lines, shaped by different strategic requirements and different lessons drawn from the First World War. The Luftwaffe had been reconstituted in the mid-1930s with a primary mission of providing close air support to ground forces. The Wehrmacht's operational doctrine emphasized rapid mobile warfare, armored spearheads supported by tactical aviation that would strike enemy positions directly in front of advancing German troops. This required aircraft that could operate at medium to low altitudes, aircraft that could respond quickly to changing battlefield conditions, and bombing techniques that prioritized flexibility and responsiveness over theoretical maximum accuracy. The Luftwaffe did develop level bombing capabilities. The Heinkel He-111 and Junkers Ju-88 medium bombers were designed for both level and dive bombing missions, but the strategic emphasis remained on tactical support rather than independent strategic campaigns against enemy industrial infrastructure. This doctrinal difference drove completely different requirements for bombsight design. German bombardiers needed sites that were simple to operate because they would often be working in single-crew aircraft where the pilot also served as bombardier. They needed sites that functioned at medium altitudes, 2,000 to 6,000 meters, where tactical targets would be clearly visible. They needed sites that did not require elaborate pre-mission calibration, because tactical missions might be ordered with minutes of notice. And they needed sites that were robust enough to function reliably under combat conditions without requiring specialized maintenance between every mission. The Lot-Fernrohr 7, introduced in 1941 with gyroscopic stabilization in the 7C variant, met these requirements admirably. It was dramatically simpler than the Norden, consisting of a single metal housing containing the majority of the mechanism, with a mirror tube extending downward through the aircraft fuselage to provide the bombardier a forward view of the target. The optical system used a mirror to reflect the target image into a telescope within the housing, eliminating the Norden's complex system of prisms and lenses. The stabilization system employed fewer gyroscopes, reducing both complexity and points of mechanical failure. The controls consisted of 3 large knurled knobs that could be operated by feel, important when working in cramped aircraft under combat stress. Most significantly, the Luftwaffe 7 allowed the bombardier to sight directly on the actual target throughout the bombing run. The Norden, by contrast, required the bombardier to initially sight on a preliminary reference point, make calculations, and then track a computed aiming point that might be hundreds of meters from the visual target. This made sense for high-altitude bombing where targets might not be clearly visible until the final seconds of approach, but it added complexity and potential for error. The Luftwaffe 7's direct targeting simplified the bombardier's task considerably, reducing training requirements and making the sight more intuitive to operate. When Oberstleutnant Baumbach and his evaluation team began their comparative assessment in late 1938 and early 1939, they brought this doctrinal context to their analysis. They were not simply comparing 2 pieces of hardware. They were assessing whether American assumptions about strategic bombing made sense for German operational requirements, whether the Norden's complexity delivered benefits that justified its significantly higher manufacturing cost and maintenance burden, and whether possessing the Norden's secrets provided any tactical advantage to Germany. The laboratory testing phase proceeded through winter 1938 and into spring 1939. Engineers mounted the Norden mock-up on a precision test bench that could simulate aircraft motion, feeding it controlled inputs of altitude, airspeed, and wind velocity, while measuring the accuracy of its bombing solution calculations. Under these ideal conditions, the Norden performed exactly as American specifications claimed. The mechanical computer calculated trajectories with mathematical precision. The gyroscopic stabilization maintained accurate reference even when the test bench was deliberately tilted or rotated. The autopilot interface responded smoothly to computed corrections, theoretically allowing hands-off bombing runs. The German engineers documented everything meticulously, filling notebooks with measurements, diagrams, and technical observations. Their preliminary conclusion was unambiguous. The Norden represented sophisticated engineering, genuinely advanced design that solved difficult problems in novel ways. American claims about its theoretical capabilities were not exaggerated. Under laboratory conditions, the bombsight performed precisely as advertised, but laboratory conditions bore little resemblance to combat operations. The next phase of evaluation would reveal whether theoretical perfection translated into practical advantage. In late spring 1939, the testing program moved from the laboratory to the bombing range. The Luftwaffe installed both the Norden mock-up and a standard production Luftwaffe 7 in identical Junkers Ju-88 aircraft. Experienced bombardiers from the Luftwaffe's bomber schools would fly multiple missions against ground targets, alternating between the two sites, with results measured and compared. The test targets were painted circles on the ground at the Rechlin-Laritz Proving Ground, north of Berlin, a facility where the Luftwaffe tested new aircraft and weapons systems. These targets ranged from 10 meters to 50 meters in diameter, representing different sizes of tactical and strategic objectives. The bombing runs would be conducted at various altitudes, from 3,000 meters to 8,000 meters, under different weather conditions, with bombardiers given varying amounts of preparation time before each run. The goal was to measure not just theoretical accuracy under perfect conditions, but operational effectiveness under realistic scenarios. The flight testing revealed patterns that the laboratory work had not predicted. At medium altitudes, 3 to 5,000 meters, where German bombers typically operated against tactical targets, both bomb sites performed similarly. The Luftwaffe 7's simpler operation actually gave it a slight edge in these scenarios, because bombardiers could acquire and track targets more quickly. The Norden's advantages in theoretical precision were offset by the complexity of its setup procedures and the time required to properly initialize its systems before beginning the bombing run. At higher altitudes, 6 to 8,000 meters, the Norden showed better raw accuracy, placing bombs consistently closer to the target center on average. The sophisticated wind drift compensation and continuous trajectory calculation delivered measurable benefits when bombing from altitudes where visual target acquisition was difficult and winds aloft could vary significantly from surface conditions. But this advantage came with substantial costs. The Norden required significantly longer setup time, approximately 3 to 5 minutes of careful calibration before beginning the bombing approach. Any changes to altitude or airspeed during this setup phase meant starting the calibration process over. German tactical doctrine, which emphasized flexibility and responsiveness, could not easily accommodate such rigid operational requirements. More problematically, the Norden proved extraordinarily sensitive to maintenance and calibration status. The device contained hundreds of precision components, gears meshing with tolerances measured in hundredths of millimeters, electrical contacts that required perfect alignment, gyroscopes that needed to spin at exact speeds. Any degradation in these components, wear on gear teeth, contamination of electrical contacts, slight imbalance in gyroscope bearings, would degrade accuracy significantly. Keeping Norden's operational in service required specialized maintenance personnel, climate-controlled storage facilities, and regular tear-down inspection cycles. The Luftwaffe 7, while still requiring skilled maintenance, was far more forgiving of field conditions and could be serviced by regular aircraft maintenance crews without specialized training. The evaluation team documented another critical issue. The Norden's autopilot integration, while theoretically elegant, created a single point of failure. If either the bombsight or the autopilot system malfunctioned, the entire precision bombing capability was compromised. The bombardier could not easily switch to manual bombing procedures, because the Norden's design assumed autopilot control during the final approach. The Luftwaffe 7, by contrast, could operate independently of the autopilot, giving bombardiers the flexibility to bomb manually if autopilot systems failed or if tactical situations required immediate weapons release without time for automated procedures. By summer 1939, as the evaluation program neared completion, the Luftwaffe's assessment was taking shape. The Norden was indeed a sophisticated device, genuinely advanced in its engineering and impressive in its theoretical capabilities. Under ideal conditions, proper maintenance, trained operators, sufficient setup time, stable flight conditions, clear visibility, and targets suited to high-altitude precision attack, it outperformed German bomb sites. But ideal conditions rarely existed in combat operations, and the operational penalties for the Norden's sophistication were substantial: complex maintenance requirements, lengthy setup procedures, inflexibility in tactical employment, and vulnerability to single-point failures. The fundamental issue was one of strategic philosophy. The Norden had been designed for a specific American doctrinal requirement: independent strategic bombing campaigns against industrial targets from high altitude under daylight conditions. It was optimized for that mission and that mission alone. German doctrine required bombsights that could support multiple mission types: tactical support of ground forces at medium altitudes, anti-shipping strikes at low level, and occasional strategic bombing when targets of opportunity presented themselves. The Norden's specialization made it unsuitable for this operational flexibility. Oberstleutnant Baumbach's final report to Luftwaffe High Command, submitted in August 1939, just weeks before Germany invaded Poland, contained a conclusion that would shock American intelligence officers when they learned of it years later during post-war interrogations. Germany, the report stated, should not attempt to copy or manufacture Norden bombsights. The device did not fit German operational requirements. Its advantages over the Luftwaffe 7 were marginal for the missions German bombers would actually fly, while its disadvantages in complexity, maintenance burden, and operational inflexibility were substantial. The Luftwaffe should continue development of the Luftwaffe 7 and focus resources on improving other aspects of bombing effectiveness: pilot training, target intelligence, and coordination between air and ground forces, rather than pursuing sophisticated bombsight technology unsuited to German doctrine. This conclusion represented a profound judgment about American strategic assumptions. The report implicitly questioned whether high-altitude precision daylight bombing made tactical sense, whether the extraordinary resources America was investing in the Norden would deliver military results proportional to that investment, and whether American faith in technological solutions could compensate for the operational challenges of unescorted bombing deep into defended airspace. These questions would be answered over the next 6 years of war. The answers would prove far more complex and far more costly than either German or American planners anticipated in 1939. The irony of Germany's intelligence windfall became apparent only as the war progressed. Hermann Lang's espionage, which American authorities would later describe as one of the most damaging security breaches in United States military history, had delivered to Germany complete knowledge of a weapon system that German military planners concluded they did not need. The secret America guarded so jealously, the technology around which extraordinary security measures were constructed, proved irrelevant to German operational requirements. But the story of the Norden bombsight's wartime performance would reveal something even more unsettling. The device that America had bet its entire strategic bombing doctrine upon would fail to deliver the precision its designers promised, its advocates claimed, and its operators desperately needed. The United States entered the Second World War in December 1941, with strategic bombing doctrine virtually unchanged from the 1920s. The Army Air Forces remained committed to high-altitude daylight precision bombing, convinced that heavily armed bomber formations could penetrate enemy airspace without fighter escort and destroy specific industrial targets with sufficient accuracy to cripple enemy war production. The Norden bombsight remained central to this doctrine. Air Force publicity materials continued to claim that trained bombardiers could place bombs in pickle barrels from 20,000 feet, a statement that was both mathematically implausible and operationally misleading. The 20-power telescope fitted to the Norden could not even resolve a pickle barrel at 20,000 feet altitude, much less guide a bomb into one. But the claim served its purpose, reassuring Congress that appropriations for strategic bombing were being spent on effective weapons systems, and reassuring the American public that precision targeting would minimize civilian casualties. The 8th Air Force began operations from England in August 1942, flying its first heavy bomber mission against rail yards in Rouen, France. These early missions, conducted against targets in occupied France with relatively light German fighter opposition, produced encouraging results. Bomb damage assessment photographs showed concentrated impact patterns, suggesting the Norden was performing as designed. Air Force commanders extrapolated from these successes, assuming that deeper penetrations into Germany would achieve similar accuracy. That assumption would prove catastrophically wrong. The first major test came on March 18, 1943, when 8th Air Force bombers attacked the U-boat construction yards at Vegesack, near Bremen, Germany. This was the first large-scale use of the Norden bombsight deep in German airspace under heavy fighter opposition and intense anti-aircraft fire. The 303rd Bombardment Group reported dropping 76% of its bomb load within a 1,000-foot radius of the target, representing a circular error probable well under 1,000 feet. Air Force Public Relations seized on these figures as validation of the Norden's capabilities and American bombing doctrine. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this, but wider statistical analysis told a different story. When results from all participating groups were aggregated, only 50% of American bombs fell within a quarter mile of the intended target. American air crews estimated that as many as 90% of bombs could miss their targets entirely, falling in open countryside, residential areas, or industrial facilities, unrelated to the mission objective. The average circular error probable across all 8th Air Force operations in 1943 was 370 meters, 1,200 feet, meaning that only 16% of bombs fell within 1,000 feet of the aiming point. For context, a standard 500-pound general-purpose bomb, which became standard for precision missions after 1943, had a lethal radius of only 60 to 90 feet. It excavated a crater approximately 9 feet wide and 2 feet deep, with bombing accuracy measured in hundreds of feet and weapon effects measured in tens of feet. Destroying point targets required extraordinary numbers of bombs. A single factory building might require dozens of direct hits to ensure destruction, which in turn required hundreds of bombs dropped to achieve those hits, which in turn required dozens of bomber sorties with their associated risks of aircraft loss and crew casualties. Multiple factors degraded the Norden's performance under combat conditions, problems that laboratory testing and peacetime training exercises had not revealed. German fighters attacking bomber formations forced pilots into evasive maneuvers during the bomb run, disrupting the stable flight conditions the Norden required. Anti-aircraft fire created similar problems, forcing bombers to fly at higher altitudes than optimal, reducing visibility and increasing the atmospheric factors that degraded accuracy. Weather over northern Europe, frequently overcast with cloud layers obscuring targets, prevented visual bombing entirely on many missions. Industrial haze and smoke from previous bombing attacks obscured aiming points even on clear days. And the psychological stress of combat operations, flying through curtains of flak while fighters attacked from all quarters, degraded human performance in ways that peacetime training could not replicate. The Norden's fundamental design assumptions baked into every aspect of its engineering, proved incompatible with operational reality. The bombsight assumed stable flight conditions during the 3 to 5 minute setup and bomb run sequence. Combat required constant maneuvering. The bombsight assumed clear visibility of the target for visual tracking. Weather and tactical conditions frequently prevented target acquisition until seconds before bomb release, insufficient time for the Norden's elaborate computational procedures. The bombsight assumed trained operators working under controlled stress levels. Combat created fatigue, fear, and time pressure that degraded even experienced bombardiers' performance. Most critically, the bombsight assumed that individual aircraft could conduct independent bomb runs, allowing each bombardier to optimize his approach to the target. Fighter defenses made this tactically impossible. Bombers had to remain in tight defensive formations throughout their missions, flying predetermined tracks that might not align with optimal bombing approaches. This forced the adoption of formation bombing tactics, where only the lead bombardier in each group actually used his Norden, with all other aircraft in the formation releasing their bombs on signal when the lead aircraft dropped. 60 to 70% of bombs dropped over Europe were thus released without any bombsight calculations whatsoever, simply salvoed when bombardiers saw the lead aircraft's bombs falling. This formation bombing technique effectively reduced the Norden to little more than a sophisticated timing device, determining when the lead bombardier should release his bombs so the rest of the formation could follow. All the complex wind drift compensation, continuous trajectory calculation, and autopilot integration became irrelevant for the majority of bombs dropped. The device that cost over $1 billion to develop and whose secrets America had guarded with extreme measures was being used in a manner that negated most of its theoretical advantages. German intelligence, monitoring American bombing operations through radar tracking and bomb damage assessment, recognized these patterns. Luftwaffe analysts noted that American bombing accuracy was statistically similar to German results using the far simpler Luftwaffe 7. The elaborate security measures surrounding the Norden, the armed guards escorting it to and from aircraft, the bombardiers' oath to destroy it rather than allow capture, the classification that prevented even photographing the device, all seemed vastly disproportionate to its actual combat effectiveness. When German forces captured intact Norden bomb sites from shot-down American bombers, they conducted their own field evaluations and reached the same conclusion they had arrived at in 1939. The device was sophisticated but unsuited to practical combat employment under realistic operational conditions. The performance gap between theoretical capability and combat results created significant problems for the Army Air Forces. Strategic bombing doctrine rested on the assumption that precision attacks could destroy specific industrial targets, crippling enemy war production without requiring ground invasion of enemy territory. If bombing could not achieve the accuracy necessary for this strategy, the entire rationale for an independent Air Force came into question. The Air Force needed the Norden to work as advertised, or at minimum, needed to maintain public belief that it worked as advertised, to justify the extraordinary resources being devoted to strategic bombing campaigns. This created powerful institutional incentives to emphasize successful missions, while downplaying systemic accuracy problems, to attribute poor results to weather or tactical conditions rather than bombsight limitations, and to continue promoting the Norden's theoretical capabilities, even as combat experience demonstrated those capabilities were unachievable under operational conditions. Post-war analysis would reveal the extent of the deception, both institutional self-deception and deliberate public relations management. The United States Strategic Bombing Survey, conducted after Germany's defeat to assess bombing effectiveness, concluded that strategic bombing had contributed to Allied victory but had not achieved the decisive results its advocates had claimed. German industrial production continued increasing through 1944, despite sustained bombing campaigns. Critical industries relocated underground or dispersed to smaller facilities that were harder to target. The German transportation network proved remarkably resilient, with damaged rail lines typically repaired within days. And civilian morale, which strategic bombing theory predicted would collapse under sustained attack, actually strengthened as the German population rallied against what they perceived as terror bombing of their cities. The survey's statisticians calculated actual bombing accuracy across the entire European campaign. The 8th Air Force, operating from England against German targets, achieved an average circular error probable of approximately 1,000 feet from an average bombing altitude of 21,000 feet. The 15th Air Force, operating from Italy against targets in southern Germany and occupied territories, achieved similar results, averaging slightly over 1,000-foot CEP from comparable altitudes. These figures represented enormous improvement over pre-war capabilities, when circular error probable measurements of several thousand feet were typical. But they fell far short of the pickle-barrel accuracy that Norden publicity had claimed and that strategic bombing doctrine required. For comparison, the survey also analyzed German bombing accuracy during the earlier phases of the war, when the Luftwaffe still conducted strategic bombing operations against British targets. Using the Luftwaffe 7 and earlier bomb sites, German bombardiers achieved circular error probable measurements, broadly similar to American results, typically in the range of 1,000 to 1,500 feet when operating at comparable altitudes under similar defensive conditions. The sophisticated Norden had not delivered the dramatic accuracy advantages over simpler German designs that would have justified its development cost and the security apparatus constructed around it. The German evaluation team's conclusion in 1939 that the Norden's theoretical advantages were marginal under realistic combat conditions had proven correct. Technical sophistication alone could not overcome the fundamental challenges of precision bombing, weather, atmospheric conditions, target visibility, defensive countermeasures, and human factors under combat stress. The story took another ironic turn when post-war interrogations revealed the full extent of German knowledge about the Norden. When American intelligence officers questioned Luftwaffe technical personnel and examined captured German documents, they discovered that Germany had possessed complete technical specifications for the Norden since 1938, had built working mock-ups, and had concluded the device was not worth copying or countering. The extraordinary security measures that had surrounded the Norden throughout the war, the armed guards, the storage vaults, the bombardier's oath, the classification that prevented public discussion, all had been largely theatrical. The secret had been compromised before the war even began. Germany knew everything about the Norden and had concluded that knowing changed nothing about their operational planning. American interrogators found this conclusion almost insulting. The implication that Germany's simpler bombsight was actually better suited to combat operations challenged American assumptions about technological superiority. But the Luftwaffe officers being interrogated were matter-of-fact in their assessments. The Norden was impressive engineering, they stated, but it solved problems that did not need solving for the missions. German bombers actually flew, while creating maintenance and operational complications that outweighed any theoretical accuracy benefits. One particularly revealing interrogation occurred in June 1945 at the Combined Services Detailed Interrogation Center at Nuremberg. Major Hans Schwefel, a former Luftwaffe bombing tactics instructor, provided detailed commentary on American bombing operations he had observed through intelligence reports. "We were initially concerned when we learned American bombers carried such sophisticated bomb sights," Schwefel stated, according to the declassified interrogation transcript now held in National Archives records. "Our pre-war evaluation suggested their accuracy would be marginally better than our systems under ideal conditions. But we also recognized that ideal conditions rarely exist in combat. When we began analyzing actual American bombing results in 1943 and 44, we found their accuracy was similar to our own results using much simpler equipment. This suggested either that the Norden bombsight was not as effective as claimed, or that combat conditions degraded its performance to levels comparable with simpler systems. Either way, we concluded we had been correct not to copy it. The sophisticated engineering was wasted in practical application." Schwefel's testimony highlighted another factor that American planners had not fully considered. Bombsight accuracy was only one variable in the overall bombing effectiveness equation. Other factors, target intelligence, navigation accuracy, bombing altitude, defensive countermeasures, weapon effects, contributed as much or more to whether a mission succeeded in destroying its objective. Germany had focused resources on these other factors rather than pursuing theoretical improvements in bombsight technology. Better target intelligence allowed bombers to attack facilities where destruction would cause maximum disruption. Better navigation systems allowed bombers to find targets reliably regardless of weather. Better crew training improved performance under combat stress. And tactical flexibility in altitude, approach, and bombing technique allowed exploitation of local conditions, rather than requiring rigid adherence to predetermined procedures. The Luftwaffe 7's simplicity supported this flexibility. Because it was straightforward to operate and maintain, bombardiers could focus on the broader tactical situation rather than managing complex equipment. Because it did not require lengthy setup procedures, bombing runs could be initiated quickly when opportunities presented. Because it could operate independently of autopilot systems, bombardiers retained manual bombing capability when technical or tactical factors prevented automated procedures. These practical advantages, while less technically impressive than the Norden's sophisticated automation, proved more valuable under realistic combat conditions. The American experience with the Norden over Japan illustrated these issues even more dramatically than operations over Europe. When Boeing B-29 superfortresses began attacking Japanese industrial targets in late 1944, bombardiers encountered conditions that completely overwhelmed the Norden's design parameters. At the high altitudes where B-29s operated, 25 to 30,000 feet to avoid anti-aircraft fire, they encountered the jet stream, fierce winds at high altitude that could add 250 miles per hour to an aircraft's ground speed or reduce it to near zero depending on direction. The Norden's wind compensation algorithms, designed for the relatively modest winds encountered over Europe, could not handle these extreme conditions. Bombs released while flying downwind with the jet stream were pushed far beyond their calculated impact points. Bombs released while flying upwind fell short. The Bombsight simply lacked the computational capability to solve the trajectory equations for such extreme wind velocities. Bombing accuracy over Japan in the first months of the campaign was catastrophically poor, with circular error probable measurements of several thousand feet. Many bombs fell miles from their intended targets, landing in rice paddies, residential neighborhoods, or open ocean. Strategic bombing doctrine, which required destroying specific industrial facilities, proved unworkable under these conditions. Major General Curtis LeMay, who took command of 21st Bomber Command in January 1945, made the controversial decision to abandon high-altitude precision bombing entirely. Instead, he ordered low-altitude nighttime incendiary attacks against Japanese cities, deliberately targeting urban areas rather than specific industrial facilities. This represented complete abandonment of the strategic bombing doctrine that had driven American air power development for 2 decades. The Norden bombsight became almost irrelevant in these operations. Bombardiers simply released incendiary clusters over designated urban areas, making no attempt at precision targeting. The results were devastating, with firestorms consuming entire city districts and killing hundreds of thousands of civilians, but they bore no resemblance to the precision strategic bombing that the Norden had been designed to enable. The final irony came on August 6, 1945, when the Boeing B-29 Enola Gay attacked Hiroshima carrying humanity's first combat atomic weapon. The bombardier, Major Thomas Ferriby, used a specially modified Norden bombsight to aim the weapon. The atomic bomb detonated approximately 600 feet from its intended aim point, the Aoi Bridge, in central Hiroshima, a targeting error of less than 1% of the bombing altitude. This represented one of the most accurate bombing attacks of the entire war. But the weapon's enormous destructive radius, over a mile for severe blast damage, made such precision largely irrelevant. The atomic bomb achieved through raw explosive power what conventional strategic bombing had failed to accomplish through precision targeting, the complete destruction of its target with a single strike. The Norden had finally been used as its designers intended, delivering a single weapon with accuracy sufficient to ensure target destruction, but only because the weapon's effects were so catastrophic that precision no longer mattered. Post-war development of bombing technology moved away from the Norden's approach entirely. The advent of radar bombing systems, which could identify and track targets through clouds and at night, provided capabilities the optical Norden could never match. The development of guided weapons, bombs that could correct their own trajectories during flight, solved accuracy problems that mechanical bombsights could not address. And eventually, the development of precision-guided munitions using laser designation and satellite navigation achieved the pickle-barrel accuracy that Norden publicity had promised, but mechanical bombsights could never deliver. The last operational use of Norden bombsights occurred during the Vietnam War, when U.S. Navy aircraft used them to drop acoustic sensors onto the Ho Chi Minh Trail in 1967. By that time, the bombsight was a historical curiosity, a mechanical analog computer in an age of digital electronics, a precision optical system in an age of radar and infrared targeting, a symbol of an earlier era's faith that mechanical ingenuity alone could solve the fundamental challenges of aerial warfare. The historical judgment on the Norden bombsight remains complex and contentious. It represented genuine engineering achievement, solving difficult problems in novel ways, and pushing the boundaries of mechanical computation and precision manufacturing. The men who designed and built it were talented engineers working at the limits of 1930s technology. But the device also represented institutional hubris, the belief that technological sophistication could substitute for sound operational doctrine, that theoretical capabilities demonstrated in laboratory conditions would translate directly to combat effectiveness, and that American engineering excellence could overcome fundamental physical and human limitations that constrained all combatants equally. The $1 billion invested in Norden development and production, an astronomical sum in 1940s currency, might have been better spent on fighter escorts for bomber formations, which proved far more effective at reducing bomber losses than any bombsight improvement, or on radar navigation systems, which would have allowed bombing in weather conditions that grounded visual bombing operations, or on larger bombs with wider destructive radii, which would have compensated for accuracy limitations through brute force. These alternative investments would have been less technically impressive, less satisfying to engineers who took pride in precision and sophistication, but potentially more effective at achieving the strategic objectives that bombing campaigns were meant to accomplish. The German decision not to copy the Norden, not to invest resources in matching American bombsight technology, proved strategically sound, even though it stemmed from different operational requirements rather than superior technological foresight. By focusing on simpler, more robust systems that matched their tactical doctrine, Germany avoided the maintenance burden and operational complications that plagued American bombing operations. German bombardiers using the Luftwaffe 7 achieved combat effectiveness comparable to American bombardiers using the far more sophisticated Norden, because combat conditions degraded both systems to similar practical accuracy levels. Technical sophistication provided marginal benefits that did not justify the associated costs. This was the uncomfortable truth that German engineers had recognized in 1939 when they examined Hermann Lang's stolen plans, built their mock-up, conducted their evaluation, and concluded that possessing America's most closely guarded secret changed nothing about German capabilities or requirements. The Norden was a solution to problems Germany did not have, optimized for a strategic doctrine Germany did not pursue, requiring resources Germany could not spare for benefits Germany would not realize. Understanding the Norden was valuable intelligence, but copying it would have been strategic folly. The story of Hermann Lang himself provides a final footnote to this tale of espionage and technological assessment. The FBI arrested Lang in June 1941 after receiving information from William Siebold, a double agent who had infiltrated the Duquesne spy ring. Lang's trial in late 1941 became a media sensation, with newspapers describing the theft of America's most vital military secret by enemy agents operating in New York. Lang was convicted of espionage and sentenced to 18 years in federal prison. He served his sentence at Leavenworth Penitentiary in Kansas, maintaining throughout that he had acted from patriotic motives, serving his homeland rather than betraying his adopted country for personal gain. Upon release in 1950, Lang was deported to Germany, where he lived quietly until his death in 1974. He never publicly discussed his espionage activities, never sought attention or profit from his wartime role, and apparently never learned the full irony of his situation. The intelligence he had provided at such personal cost, the plans he had stolen so carefully, the technical knowledge he had shared so thoroughly, had been deemed by the recipients as interesting but not particularly useful. His espionage had been successful but strategically irrelevant. The broader lessons from the Norden bombsight story extend beyond World War II technology into fundamental questions about how military organizations assess and adopt new capabilities. The bombsight represented a classic case of requirements mismatch, where a technically sophisticated solution was developed for one set of operational conditions, but then employed under completely different conditions, where its advantages could not be realized. The elaborate security apparatus constructed around the Norden reflected institutional psychology more than rational security assessment. By classifying the device so heavily and surrounding it with such extreme protective measures, the Army Air Forces created a perception of extraordinary value that may have exceeded the device's actual combat contribution. This perception became self-reinforcing, justifying continued investment and preventing honest assessment of whether the Norden was delivering value proportional to its cost. When German forces captured intact Nordens from shot-down bombers, American commanders assumed this represented catastrophic intelligence compromise. In reality, Germany already possessed complete technical knowledge and had concluded that knowledge was not particularly valuable. The security breach had occurred years earlier, but its consequences were far less severe than anyone had imagined because the secret being protected was less important than the protection suggested. The German evaluation team's assessment methodology offers lessons for how military organizations should evaluate new technologies. Rather than focusing solely on laboratory performance or theoretical capabilities, the Germans emphasized operational context. How would the technology actually be employed? Under what conditions? By what users? With what support infrastructure? They recognized that technical sophistication could create maintenance burdens and operational complications that offset theoretical advantages. They understood that combat conditions degraded all systems, and that robust simplicity often performed better than fragile sophistication when equipment was stressed by battlefield realities. These insights allowed them to make sound judgments about whether to invest resources in copying or countering the Norden, even though those judgments contradicted the prevailing assumption that more sophisticated technology was inherently better technology. Modern military technology development still struggles with these issues. Sophisticated weapons systems promise revolutionary capabilities under ideal conditions, but often fail to deliver proportional advantages in realistic combat environments. Maintenance requirements exceed planning estimates. Training pipelines cannot produce enough qualified operators. Support infrastructure proves inadequate for deployed operations. Combat conditions degrade performance in ways peacetime testing does not reveal. These were exactly the problems that plagued the Norden bombsight, and they remain challenges for contemporary systems despite decades of institutional experience that should have taught better acquisition practices. The Norden bombsight story ultimately illustrates that wars are decided by the effective integration of technology, doctrine, training, logistics, and leadership, not by technical sophistication alone. America won the strategic bombing campaign over Germany, not because the Norden was a superior bombsight, but because America could build bombers faster than Germany could shoot them down, train crews faster than they could be killed, and sustain losses that would have broken any other nation's will to continue. The bombsight was one element in that larger system, and not necessarily the most important element. Fighter escorts, logistics, intelligence, and sheer industrial capacity mattered more than bombsight accuracy. Germany recognized this in 1939 when they evaluated the stolen Norden plans. America learned it gradually through 5 years of costly combat operations. That Germany recognized it first, but still lost the war, demonstrates that correct technical assessments alone do not determine strategic outcomes. Wars are won by nations that can mobilize their entire societies for sustained effort, not by nations that make the best decisions about individual weapon systems. But understanding why Germany dismissed the Norden while America venerated it reveals fundamental differences in how the two nations approached military technology, differences that extended far beyond one device and shaped their entire conduct of the war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.